today lecture is going to be a bit unusual because it will contain, it will consist of few short stories. So we start with experimental facts, which precede the discovery of phenomena which is called superfluidity. So we are still talking about interacting both a gas or liquid. So let's start from few historical remarks. So first, in 30s, people start to do experiments with the liquid helium. So I'm talking about isotope helium-4. So, and what was discovered is that specific heat showed quite unusual behavior. Namely, at some temperature, precisely 2.18 Kelvin, there was a cusp in a specific heat. So specific heat behaved like that. Moreover, this cusp was fitted by a logarithm, and it fitted well, while below critical temperature, and this is critical temperature, behavior of specific heat corresponded T cube, behavior characteristic for phonons, as we all know. Then, in yet another brilliant experiment, Professor Andronikashvili from Georgia used a stack of disks put in a container with liquid helium at temperatures below T naught. This is a T naught. And then he made a torsion of this stack of a disk. So this is a container filled in with liquid helium. So he just moved it this way in order to measure momentum inertia. And this measurement showed that the inertia momentum which he measured did not describe by the theory of liquid, which people suppose helium-4 was. Then there was an interesting experiment which was called Fontaining effect. Again, there was a container, there was a liquid helium inside, and there was a pipe of that form inside liquid helium. The liquid was cold. The area around container was hot. So hot means warmer than the liquid. And then there was a fontaining of the flow from cold to hot. So this was Fontaine effect. Again, this is helium-4. And this is helium-4. And then there was yet another measurement when two containers were connected to by a capillary. So in the first container, there was a temperature T1 and pressure P1. And in the second container, there was a temperature T2 and pressure P2. Moreover, the temperature 2 was higher than temperature T1, and pressure 2 was higher than T1. So this is a cold container, this is a hot container. What we normally expect when there are two containers with a hot and cold substances, for example water, we expect that the hot substance goes inside the cold container to make it warm. However, here it was other way around, namely the cold substance went to the hot container to become it colder, to make it colder. So this is so-called thermomechanic effect. All this demonstrated that liquid helium below temperature 2.8 in Kelvin behaves very unusual. And in order to explain this behavior, it was suggested that below temperature T node, liquid helium consists of two liquids, or two-component liquid. So first of all, there was a normal component. This is T node, which was the only component for temperature. This is temperature, this is the density, which is the only component above temperature T node. And then there was a superfluid component, rho S and rho M. So below temperature T node, there is also superfluid component, which is responsible for this property. And moreover, in addition, people discovered that if liquid helium is pushed through the capillary is pipe with a small diameter, then it flows without friction. All this together resulted in discovery of phenomenon which is called superfluidity. The paper with this name, the name of this effect, was published in 1937 by Piotr Kapitsa, Cambridge, and since that time the word became standard for description of this phenomenon. In 1973, I think, the Nobel Prize was given to experimentalist Piotr Kapitsa for discovery of phenomena of the superfluidity. Okay, but of course, well, a lot of theoretical works done in this direction in order to understand it. And today we are going to discuss quickly the most important ideas related to this phenomenon. Okay, I erase all this. Of course, it was understanding that what was observed in experiment is quantum property of quantum liquid, and moreover, since phenomena of Bose-Einstein condensation was suggested in the works of Einstein and Bose in 1924, people immediately understood that this superfluidity has something to do with Bose-Einstein condensation. However, it was also clear that it's not really this ideal system with Bose-Einstein condensate suggested by Bose and Einstein, and it took almost 60 years in order to find a system which possess these properties of Bose-Einstein condensation, and this discovery was done in the diluted gases of alkali metals. We are going to see slides on Wednesday, and also I explain why it took so long between theoretical prediction and experimental discovery. To cut a long story short, I would say that liquid helium, although the phenomena which I'm going to discuss indeed related to Bose-Einstein condensation, is far from being ideal because the system appears to be characterized by strong interaction. And during last two lectures, we discussed weakly interacting Bose gas. So the fraction of the condensate is of the order of 10%. And therefore, it's not that ideal system like alkali gases, where the fraction of condensate at zero temperature is of the order 99.99%. Okay, so let me make a side remark. In order to describe this phenomenon, Landau suggested phenomenologically that spectrum of excitations in the liquid helium has this interesting form. So this is epsilon P and this is P. First of all, we recognize phonon mode. So this is sound velocity, Cp. And this is low-lying branch of excitations. These are phonons. However, in order to describe the experiment, there are many more observations, like entropy wave, second sound, third sound, and so on and so forth. There was prediction that there is additional minima in the spectrum around some moment P node, and this branch spectrum was separated by the gap, and the branch of excitations around P node was called rotons. And as we will see, these rotons have something to do with the creation of vortices, which we are also going to discuss briefly today. Okay, now the story number one is called Landau criterion of superfluidity. So, in order to understand when we can have a superfluidity, namely ability of liquid flow through the capillary without friction, let's do some mental experiment. Let's assume that this is a capillary. Of course, I'm drawing sort of exaggerated cartoon, and there is a flow of liquid along this capillary. In order to derive the criteria and understand the criteria, let's discuss two coordinate systems. One coordinate system will be associated with a capillary attached to the wall, and this is laboratory frame, and another coordinate system will be associated with a liquid. So this coordinate system will move with a constant velocity, and I'm assuming that the liquid flows with a constant velocity, and I will be so-called sitting on this liquid. So what does it mean, friction? We are saying that the liquid flows without friction. Friction means that the liquid actually irradiates some phonons which are accepted by the walls of capillary. In such a way, the energy of the liquid becomes less, and therefore the liquid slows down. This is how liquid works. So the criterion is actually about to find a condition when the liquid cannot emit the phonon inside the wall of the capillary. Actually, theory of friction is very interesting by itself. So, what Landau said? We are talking about quantum liquid, which we are going to characterize by the moment. Let's write down the energy in two systems. So the energy, so this is system 2 of pipe. This is system 1 or flow. The energy in a system associated with the walls of capillaries, pipe, is equal to energy in the system, in the coordinate system associated with flow, plus P dot V. I assume that V is velocity, plus m w squared over 2. So this is a kinetic energy. I'm talking about energy of the excitations. So namely, I'm talking about excitations in the coordinate system associated with the flow. And I will call it E T. Since in the coordinate system of the flow, momentum will have opposite sign. So P prime is equal to minus P. In order to be able to emit phonon, I should have my energy in the system associated with the capillary being less than kinetic energy, mw v squared. So E prime P minus P V should be negative. Or my velocity should be larger than E prime P divided by P. So if this criteria is fulfilled, then there is a friction. So this is criteria to get energy losses. Namely, if my flow moves with a velocity larger than that, then I emit phonons and walls of the capillary accept it. Let's consider a few examples. And of course, this criteria should be valid for infinitesimally small momentum of the motion. So this criteria should be valid also in the limit p goes to 0. So then, example number 1. Suppose that we have ideal Bose gas, no interaction whatsoever. Then the energy of bosons Et prime is equal to p squared over 2m. If I plug it in the criteria of emitting phonons, and this is precisely Landau criterion, I will get that critical velocity, which is E prime P divided by P, is equal to P over 2m, and it goes to 0 when momentum goes to 0. So the first observation is that the ideal Bose gas, namely Bose gas without interaction, is not superfluid, because for any arbitrary small velocity, the Landau criterion is fulfilled, and therefore the liquid emits phonons inside the walls of the capillary. Let's consider example number 2. The Bose gas with interaction. And as we discussed it on Friday, the lowest lying excitations, phonons, are described by spectrum epsilon prime p. Therefore, the subindex C is equal to E P prime divided T is equal to C. Bingo? Now we see that if flow moves with a velocity smaller than the sound velocity, then it's superfluid. It doesn't produce any friction. However, if the liquid moves with velocity higher than the sound velocity, then the superfluid is destroyed and we have a friction. Actually, this phenomena is of very high importance. We will see in the next chapter, when we discuss superconductivity, that this is precisely what happens in the superconductors. Namely, if you have superconductor and you want to create a current, so you use wires in order to conduct current between source and drain, you see that this current associated with some velocity of of object which superconduct, if this velocity of this current is smaller than critical, then the superconductivity is preserved and you can conduct electric current without energy losses. However, if you increase the current density more and more, you come to some threshold and the threshold tells you that for currents larger than critical one, you destroy the superconducting state. So one of the challenges of modern science is to find materials which possess superconductivity properties at sufficiently high temperature, which actually keep superconducting state not destroyed at sufficiently high magnetic field. We see what is effect of magnetic field, an equivalent effect in the superfluid liquid, and so to have a material which can conduct current at relatively high densities. Therefore, for practical use, you need to get such material in order to make wires, in order to make superconducting magnets for many, many applications. So you see that the problem which we start to discuss today has not only very important scientific value, but is also very important for the applications. And then, number 3, what happens and how Landau criterion works for the spectrum like that. It appears that one needs to plot tangential, and this tangential will give you a critical velocity and below which your liquid, which possess both phonon branch of excitations and roton branch of excitation, remain superfluid and can flow through the capillaries without friction. The same criteria and the same style of two-component liquid can be applied to explain non-classical inertia momenta in the Andronikashvili experiments. It can be applied in order to explain the thermomechanical effect, which I noticed, which is related to entropy waves and to Fontaine effect. For those who would like to learn more about superfluidity, I strongly recommend book of Isaac Halatnikov, with a simple title, Theory of Superfluidity. So Isaac was a great scientist who contributed a lot to the theory of superfluidity from the first momentums of discovery. Unfortunately, Isaac passed away 3 weeks ago at the age of 101. So you see, the great physicist made a great contribution, had a long, interesting, and very productive life, and wrote a fantastic book of theory of superfluidity. Okay, so now let's elaborate on quantumness of the liquid and see what kind of theory we can construct based on what we have already learned about coherent phenomena known as Bose-Einstein condensation. Okay? So, let's be back to our first lectures about Bose-Einstein condensation. We said that for sufficiently low temperatures, we can characterize the many-body state associated with a Bose-Einstein condensation with unique wave function. So this is a wavelength. I remind you, this is a de Broglie wavelength. And below temperature of condensation, remember that for weakly interacting Bose gas, the temperature of Bose condensation doesn't depend on interaction. corrections will. So we see that below T node, the Broglie wavelength becomes much larger compared to the distance between particles. And therefore, we can say that the wave function, again, this is a many-body wave function, which is no more a product of single particle wave function. Please don't be confused. We describe this giant matter wave or giant coherent state with a unique wave function, which has a modulus. So this is a modulus, is a square root of n node, which depends on R over D, times phase factor. On the first lecture, I denoted this phase by the letter phi. Now I would like to use notation of chi, which also depend on R. So this is a giant matter wave, and you remember that we said that suppose we have Bose gas in the quantum well, I can use the walls, hard walls, infinite walls. So this wave function RT, RT, RT is obtained from the solution of Gross-Pitayevsky equation. I remind you that this is I h bar deep psi over dt is equal to minus nabla over 2m h squared plus g psi squared minus mu psi. So this is Gross-Pitayevsky equation or nonlinear Schrödinger equation. If we consider potential of that sort, we see that first of all we get a contact density. So G times psi square minus mu is equal to 0. So which says that the constant psi modulus square is a constant. Therefore, we can say that the density and I denote n node R T over V. This is a stationary solution, of course, where the derivative, time derivative. This is a density and node is constant. You may ask me how I can simultaneously have constant density. So this is a well and boundary condition which tells me that at the walls the wave function should be equal to 0. I tell you the answer, and those who would like to learn more, please read basic book. Actually, what happens is that there is certain lens, which is called healing lens. At which wave function goes down and acquires 0 values. However, apart of the small area around the walls, I can indeed consider my condensate being characterized by constant square modulus of the wave function. I deliberately write square modulus because there are effects associated with the phase. Let's write the current, the quantum mechanical operator of the current. So the current is equal to I h over 2m, and then I have a psi nabla psi dagger minus psi dagger nabla psi. This is a quantum mechanical operator of the current. Well, in a sense, this is also operator, operator, but I will be talking about expectation value of this current, so some function. Okay, if we plug in this form of the wave function, what we will get, we assume that we are not around the walls of the containers. So being far away from it, well, not far away, a bit distant, on a distance of Hilling length. So therefore, I assume that the density is constant. So I don't differentiate the density. I differentiate only exponent. So this is I h bar n node divided by 2m. Here I have e to the power I chi. Now I apply my Nabla operator to exponent complex conjugated. So this is then e to the power minus I chi Nabla minus I chi minus e to the power minus I chi e to the power I chi Nabla applied to I chi. So what I see that the exponents, the product of two exponents give me 1, and what remains is gradient of phase. Minus I times I gives me 1, and I have two similar terms, which tells me that the current is equal to H over M n node times Nabla chi. So the current in a superfluid system is associated with a gradient of phase. And of course, since current is n node times superfluid velocity, I can write down that the superfluid velocity is h over m gradient of chi. Good. This is the first conclusion which we draw from the fact that our Bose system is described in terms of gigantic matter wave below the Bose-Einstein condensation transition temperature, and we can describe this gigantic matter wave by unique wave function. Okay? Now let's see what are the consequences of having this form of the current and velocity. Let's recall mathematics, and if we have field described by the gradient on some function, and we are computing circulation of this field, I remind you that this is the same as rotor Vs or curl Vs. We know that the integral over Nabla times, let me be not that fast. In our case, Vs is a gradient chi, so Nabla times h over m gradient chi is equal to 0, because the curl of the gradient is equal to 0. So to say, you have a vector product of two Nabla operators. Okay? Therefore, if we recall the Stokes theorem, then Nabla times Vs ds we have flow through some area. So this is a normal to this area, and ds is normal times ds. So this, according to Stokes' theorem, is equal to the integral over contour, which confines this surface Vs dl. Okay? But if we have a potential flow, on the left-hand side we have a 0, because this operator gives me 0. So therefore, in right-hand side, I should also have a 0. However, this is not the only possible solution. Again, suppose we have a container. We have a container. We have superfluid liquid inside it, and we start to rotate this container. Let me look from the top of this container. I can have potential flow everywhere inside this area. Therefore, I can write down that integral along contour 1, this is a contour 1, C1, this is C2, Vs dl is equal to, well, plus actually integral over contour C2 Vs dl, and this is equal to 0 because we have a potential flow in this area. So you see that integration over contour C1 goes anti-clockwise, and integration over contour C2 goes in a clockwise direction if I will make directions the same, and I will take into account that Vs is actually tangential velocity. As usual, what I can write is 2 pi r1 times Vs r1 minus 2 pi r2. This is this integral. Vs over r2 is equal to 0, which means that Vs r1 times r1 is equal to Vs r2 times r2. So therefore, my superfluidity velocity has a singularity at r equal to 0, namely Vs is proportional 1 over r. So there is some object which people call vortex, which is created in the middle, in the center of container, when you rotate it with an angular velocity higher than certain velocity. So at the end of the lecture, we will derive sort of Landau criterion, generalized Landau criterion, or how fast we should rotate our container in order to create the singularity. So vortex is actually topological object, which appears just because of topological properties of our quantum liquid. And these topological properties were known well long time ago and discussed long time ago, before people now, for example, start to consider topological method, topological effects in different quantum substances. So this is probably one of the first examples when topology plays a very important role and results in the interesting case. So what we are going to do now is to see that this phenomenon would actually result in quantization of circulation. Let me show you how it works. Of course, if you rotate container slow enough, you will create nothing. you need to overcome some thresholds in order to create first vortices. And when you rotate faster and faster, you will get more and more vortices, and as a result, you will get so many vortices that your superfluidity is destroyed. Because in the vortex, so this was my container. So what happens? So you have this vortex associated with rotation. As I said, in the core of the vortex, the superfluid velocity becomes very high. So it actually violates Landau criterion. So the core of the vortex, so this is the core, is a normal liquid, and outside we still have a superfluidity. When we have more and more vortices, you have more and more normal component inside the liquid and less superfluid, and finally you destroy superfluidity completely. And we will see that in superconductivity, which will be associated with a charged substance, which superfluid and superconduct current, the equivalent of rotation of the container is played by magnetic field. We will see that there are type 1 and type 2 superconductors, and in type 2 superconductors, in type 1 superconductors, magnetic field doesn't penetrate in the superconductivity. This is Meissner effect. We will spend a lecture to discuss why it happens like this, but in a type 2 superconductor, magnetic field creates vortices. Vortices form lattice. Actually, it appears that the lattice of vortices is triangular lattice, and with more and more magnetic field, superconductivity is destroyed. And again, the theory of vortices and superconductors was created by Alexei Abrikosov, who was at that time 26 years old, and 50 years later, he got a Nobel Prize for this discovery, which has actually extremely important technological application. Good. So, circulation and quantization of circulation. So, in order to derive this quantization, we assume that we have a cylindrical container. For all what I'm going to say today, we are discussing cylinder. So, in this sense, this is z-axis along the direction of the cylinder. This is y and this is x. But it is more convenient, since we have a cylindrical symmetry of the problem, to use cylindrical coordinates. Namely, instead of writing x and y, everything is isotropic in the direction along the axis z. We write x is equal to r cosine phi, y is equal to r sine phi. So in the xy plane, xy, we have r and we have phi. So tangent phi is equal to y divided by x, and r modulus is equal to square root over x squared plus y squared. And z remains the same as for Cartesian coordinate system. Let's write operator number in the cylindrical coordinate system. So operator number is equal to, we have now 3 orts. So we have ort along z, we have ort along r, and we have ort along phi. So nabla is equal to LR d over dr plus 1 over r d over d phi L phi plus L z d over dz. Without losing generality, since I told you that the velocity is tangential, for my wave function psi which is square root over n known e to the power I chi. Without losing generality, I can say that chi is equal to 5 with a some coefficient, a known coefficient alpha. Yeah. You see? So, what does it mean? If I plug in, you remember that Vs is equal to H over M nabla chi. So from this connection, I obtain that Vs is d over d phi. So everything depends only on phi. Nothing depends on r and nothing depends on z. So this is H over 2m, sorry, H over m alpha phi. So alpha, sorry. Sorry. Not so quick. It's 1 over r, d over d phi. So this is alpha divided by r. I'm looking for this solution. So this is operator nabla. Nothing depends on the r. Nothing depends on the z. We have nabla applied to chi. Chi is equal to alpha phi. We have 1 over r and alpha. Good. So we already found right functional behavior of our superfluid velocity, but let's remember that this function should be periodic when we change phi to phi plus 2 pi. If we look at this, we see immediately that alpha should take integer values. Otherwise, we will not get this periodicity. Periodicity means that we make first circle, second circle, and so on and so forth. Therefore, we come to a very important conclusion that alpha can take only integer values, s, which is 1, 2, 3, and so on and so forth, which are called winding numbers. So we obtain that the superconducting velocity is h squared over m, s divided by r, where s is equal to 1, 2, 3 integer number. Therefore, we have a quantization. Good. Let's now calculate the integral. We calculate gamma, which is integral Vs dl. Again, we have a cylinder. Our top view velocity Vs is tangential to the circle, and therefore this integral is equal to h over m times s over r times 2 pi r, the length of the circle. Therefore, gamma is equal to h over m times 2 pi times s, because r cancels out. So we have a h over m, because this is h times s. So the circulation, namely the integral taken along the circle, is quantized, and this is the circulation quantity. gamma naught. And the S is integer number. So we got the quantization of the superfluid velocity, and we got the quantization of circulation. Let's make two more calculations, and then I will be answering to your questions. The calculation number one. Again, I'm doing very simple exercises on the blackboard. But each of these exercises leads to very important conclusions. Let's now, without losing any generality, on very general ground, discuss how the vortices interact. And we got it just from symmetry reasons. Let's compute the inertia moment. Again, we have a superfluid flow, which flows like that. Velocity is tangential. Momentum is r dot p. Therefore, if velocity is tangential, r is radial, then the vector product tells us that m is equal to mz times ez. So the inertia momentum is directed along the axis in this cylindrical geometry. So therefore, mz is the only component, and we compute it. We consider the cylinder of the height L. So this is the L. This is integral from 0 to r naught. The diameter of the container. We have r dr. We have integral from 0 to 2 pi d phi. And we have r dot p. So we have, therefore, r times p is the superfluid density times superfluid velocity, which is h over m s divided by r. So we need to compute this integral. Integration over phi can be done in a very simple way. So this is L times superfluid density rho s times 2 pi integral over d phi times h over m times s, and remains integral r dr from 0 to r naught. We have r naught squared up. So therefore, I will reshuffle my multipliers. So this is L times pi r naught squared times superfluid density times h over m times s. This is the volume of container. So this is the volume. This is the density, which is mass times mass per unit volume, and we have a mass here, therefore it will be some large integer number. So this is h over m, some n, s, where n is rho s times volume divided by mass. This is a mass. So what did we learn is that mz is proportional to s, proportional to the winding number. Okay? Let's calculate the energy. Energy. With the same way, we consider cylindrical container. So this is L times integral R node. Let me put some interrogation sign at low limit. I will explain why. R dr integral from 0 to 2 pi d phi. And then I have rho s times ds squared over 2. So this is energy, m squared half, which is integration over phi can be done without problem. 2 pi L integral R dr rho s, and we have 1/2 h over ms squared times 1 over r squared. So cancels out, and we see that the integral which we have at the end of the day has a form dr divided by r. So the integral diverges logarithmically. Therefore, we need to cut our integral on the lower bound by some parameter a, and a is of the order of size of the core of the vortex. So what we have altogether, this is pi rho s L, because 1/2 cancels out, h square s over m square times log r over a naught. So we see that the energy actually contains logarithm. And as a result of this logarithm, there is yet another interesting physics associated, for example, with Kosterlitz-Tauris transition. This logarithm is called Vortex logarithm, and yet another Nobel Prize winner. Nobel Prize was given to two gentlemen, Kosterlitz, David Kosterlitz and Tauris, and being at ICTP, you already participated in the colloquium of Kosterlitz, who explained you also historical background of discovery of the Kosterlitz-Tauris phase transition, which actually yet another universality class and very important contribution. So today I already mentioned 3 Nobel Prizes. On Wednesday, when we discuss cold gases, I will mention another couple of 3, 4, 5 Nobel Prizes given for discovery of Bose-Einstein condensation, discovery of methods, efficient methods of cooling, and so on and so forth. Good. So let's combine these two things together in order to find out the criterion for the creation of the vortex. Okay, what I need to know is that momentum is proportional to S, and energy is proportional to S squared. This is the first observation. What kind of conclusion we can draw from just this observation? If we have, first of all, the creation of vortices with large winding number is not energetically favorable. Because if we have 2 vortices with a S equal to 1, the energy will be 2 times S squared, 1 squared. However, if we create a vortex with a winding number S equal to 2, then the energy will be 2 squared equal to 4. So creation of one vortex with large quantum number, larger than 1, is not energetically favorable therefore, when you rotate the container, you start creating vortices with a winding number equal to 1. Good. Second, suppose we have two vortices, say S1 and S2. The energy, suppose these two vortices come together and form one vortex with a winding number S1 plus S2, because there should be conservation of momentum and conservation of energy. So energy of S1 plus S2 is proportional S1 plus S2 square, and actually is larger than ES1 plus ES2. Therefore, two vortices, if they come closer to each other, cannot merge and create vortices with large winding number. Therefore, vortices repel each other. So the interaction between vortices when they approach each other is repulsion. And we got it just from, I would call it topology, from topological properties, from the quantization of the velocity and from the quantization of circulation. Therefore, if we have a vortex 1 and we have a vortex 2, so you see here it goes in this direction, here it goes in this direction, so, and they repel each other. If we have many vortices like that, they all go along the same direction. So therefore, whatever system of vortices you get, because you create this by winding, what you will get at the end of the day, this envelope function, where the quantized circulation will appear, and everything inside is cancelled out. And vortices would like to keep distance between them, so there is no way to collapse, there is no way to have a singularity in this system. Okay? Good. So, last calculation. Today we finish probably a little bit early, although I will reserve time for questions, but many other lectures we finish a bit late. So we take a container and we start to rotate it with angular velocity. So here, contrast to derivation of Landau's criterion, when we considered two inertial systems, so the system was Galilean invariant, so we consider one system associated with the wall and one system associated with flow. Here, by rotating container, we are dealing with non-inertial coordinate system. But still, the arguments are the same. We need to compare E prime and minus momentum times angular velocity. So m is not mass, m is momentum. So since we rotate container this way, angular velocity goes this direction, inertia momentum mz goes to this direction, and this should be negative. So the critical velocity, omega, should be larger than omega c, which is equal to E prime divided by the momentum, mz. Suppose we want to find out the angular velocity necessary to create only one vortex, which appears in the middle of the container. So in my calculations, I assume S equal to 1. So therefore, this is L H over M squared times pi times logarithm R over A divided by pi L R node square H over R, and that's it. There is rho S here, there is rho S here. So L is cancelled out. 1 power H over M cancels out. Pi cancels out. Rho S cancels out. So the critical velocity for creation one vortex is equal to H over M R node square times logarithm L over A. Okay, good. You may ask me what physical the parameter A is. Well, R node, of course, is macroscopic parameter, is centimeters or millimeters, but we have a log, and log is a very, very slow function. So even if A is of the order of lattice constant, interatomic distance, which is of the order of angstroms. Angstrom is 10 to the power minus 10 meter. So if we have container of 10 to the power minus 2 meters radius, which is 1 centimeter, 10 to the power minus 2 divided to the 10 to the power minus 8 gives them 10 to the power 6, and logarithm of this is 6 logarithm 10 is just something of the order of 10. So this means that whenever you see log, it doesn't matter so much what the upper bound and lower bound, provided that the ratio is very large number, but log just gives you number of the order of 1, or in the best situation of the order of 10. Okay, that's all for today. I finished with my lecture, and I'm ready to answer your questions. As I said, today we have a bit shorter lecture. Good. So no questions. Everything is clear. Well, now, as I promised problems for this lecture, I will also test it and send it, but maybe when I accumulate another 10 or another 12 problems. So 2 problems for today. Consider Landau spectrum. Which is epsilon p is equal to Cp for p smaller than p node, and delta plus p minus p node squared over 2m for p around p node. So this is a p node. These are phonons and these are rotons. So consider thermodynamics of phonons, namely, if you consider linear spectrum, what will be entropy, what will be energy, entropy, and specific heat. Basically, you need to do nothing because you know it from the course of electrons and phonons, that for specific heat and for entropy, you will get T to the power 3 contribution. This is a linear spectrum. However, what's interesting is to consider contribution of rotons. to the spectrum, to the thermodynamics. So please compute what kind of addition to specific heat and entropy will be originated from Rotten minimum of the spectrum. And of course, for those who would like to read more about phonons, rotons, phenomenology of superfluidity, in addition to the brilliant book of Kalatnikov, I would strongly recommend to read Richard Feynman book, which is called Statistical Mechanics. The last chapter of Statistical Mechanics is fully devoted to the discussion of superfluidity, and Feynman himself was a brilliant scientist who obtained a Nobel Prize and who made a contribution to different branches of physics, to high energy physics, to solid state physics, and it's very difficult to overestimate his contribution to the theory of superfluidity. There you can also read about different sound waves, about rotons, and if you will not succeed to obtain this contribution to thermodynamics, you will find answers in Feynman book. Let me write it again. So Richard Feynman. Start. Yeah. This book had many, many editions, and both books are available in the ICTP library. Okay, 2 problems for today.
Hi, Professor. I have a question.
Yes, please.
So, is superfluidity and condensation like related? They need to happen at the same time or not?
Well, in order to create superfluid state, you first need to have a Bose-Einstein condensation. So you need to have this giant matter wave. But what I told you that not every Bose condensed system is superfluid. So superfluidity is basically more than Bose-Einstein condensation. Bose-Einstein condensation is necessary condition, but not sufficient condition. So you need to have Bose-Einstein condensation plus weak interactions in the system. Then you will get superfluidity.
I understand. Thanks.
Okay, more questions? So if not, we are done for today. As I said, on Wednesday, we will have a lecture with the slides. Slides will also be available after lecture for you. Everything what we discussed with the slides will not be included in the exam, for sure. However, it doesn't mean that you can skip this lecture and they give you a waiver not to be present. It's other way around. I think we will be discussing interesting and modern stuff. So I'm going to review, first of all, the experiments with alkali metals, which was the first actually evidence, which provided the first evidence of the discovery of Bose-Einstein condensation phenomena in non-interacting system. And then we discuss ways to confine the gas of bosons either in magneto-optical traps or in the optical lattices. And we will see that this alkali metals, this gas below Bose-Einstein condensation transition, is very nice playground for many interesting phenomena, including phenomena related to high temperature superconductivity, strong correlated system, metal insulated transition, which we are going to study in more details in the second half of the course, and also very important for applications in metrology, in quantum computing, and so on and so forth. So this is planned for Wednesday. I don't know if I will be lecturing from the room or I will be lecturing from home. I don't expect any need of the blackboard. Let's see. but it's going to be slide lecture and also summary of what we have discussed during previous 9 lectures. So lecture on Wednesday will conclude the first half of the course, first 10 lectures, and next week we will start with theory of superconductivity, but before coming to superconductivity, I will spend 1 or maybe 2 lectures for the crash course of the phase transition theory. This is the plan. Okay, good. If there are no more questions, that's all for today.
Thanks. Bye.